Thank you. So, welcome to the last session of today. My name is Victor. I'm a software engineer at Red Hat, but I've been also involved with local universities for a long time, so I'm gonna chair this session. The session will be slightly different from the previous three because we will have not two but three talks. But don't worry, after the three talks there will be meal and everything. So yeah. In this session we will cover two topics that haven't been covered so far. One of them is IoT, Internet of Things, and the other one is software testing. So hopefully you will enjoy. Our first speaker will be Professor Frédéric Lemuel from National Institute of Applied Sciences in Lyon. He is leading the Center of Innovation in Telecommunication and Integration of Services at this institution, which falls under the University of Lyon. His research covers a lot of different areas and topics, and one of them is research in dynamically adapting and autonomous environments, about which I presume he will talk today in his talk. So, Frédéric, the stage is yours.
Okay, so thank you for inviting me. So that's really a pleasure to be there. There are so many interesting presentations. So first, I would like to thank the other people that have contributed to this work. So my PhD students and colleagues from Red Hat, so Julien Ponge and Clément Escoffier. So first, Lyon. I'm coming from Lyon. So I don't know where is Lyon, but it's 2 hours from Paris by train. And you have great sectors in electronic and IT services. So that's why I will talk about IoT today. But I invited you also to come to test the gastronomy in Lyon. So I'm heading the City Lab. So the City Lab is a laboratory in telecommunications. So we are more than 100 people, and we are collaborating with Nokia, with Orange, and SPI, national company in IT services, and we have common labs with this company, and we are focusing a lot of on experimental approaches, so a lot of platforms. Especially we have one radio frequency anechoid chamber where we can test every kind of signal processing and distributed computing without any interference. So in the same way we have seen this morning. So basically, we are working on the different layers of telecommunications. So from the antenna, signal processing, radio communication, embedded systems, networks, robots, distributed system, and security and privacy for all these layers. Right now, the main topics we are focusing on are modeling complex system with deep learning, reinforcement learning, and quantum communication. So where we can't model everything because the space to discover is too large, we are using a deep learning approach. We are working also on large-scale systems, so 6G, IoT, fog edge computing. And just because the system are so large, we need to let the system collaborate together. So we are also working on blockchain, autonomous fleet of robots, cars, and systems that has to respect different legacy requirements. So I'm heading the lab, and I'm the holder of 2 shares, so in the Internet of Things and also in Edge AI. So I will show you at the end what we can work on. And personally, my interest is to work on distributed systems, and right now, distributed systems at the border of the network, so edge and fog computing. So in this kind of environment, so working in dynamic environment, the interesting characteristics you can find are these three properties. We have to deal with systems that need to save energy. We need also to handle mobility, disconnections, and we need to have very large-scale systems. And in fact, all use cases we are talking about, so IoT, mobile cloud, car fleets, etc., have to deal with these characteristics. So when you want to build a system for such kind of environment, it's quite difficult to handle every part of your system. So as we have seen today, you can work on the network part or on the OS part, but at the end, finally, you have to integrate all of this. And integrating operating systems, distributed systems, to program these systems, optimize and deploy algorithm is finally very, very complex. So the vision we are developing is to do this adaptation at two different layers, either in the small and either in the large. So when you are developing and deploying IoT application, in fact, you need to handle and you need to know how to deploy from the low level to the very large level. So optimizing the network is not enough. You need to know also how to optimize your embedded system and your services. So let's illustrate this with a project, an ongoing project we have with the SPI company in France, and it's a PhD also co-supervised by Julien Pauge from Red Hat. So let's take a classic dataflow application. So you are grabbing information from, for example, a building or from a car, and you want to fetch this data, you want to filter, to do some processing on your data, and you have a classic, in fact, chain of operators, so to do your filter, map, reduce. And the question behind is, okay, where do I deploy these operators? And you can deploy this operator in a cloud, but in that case, you know, you're not completely aware of what's happening inside all your network. You're sending all your data. So with edge and fog computing, the idea is to move these operators, to move this processing at the border of the network, so that you can benefit from good latency. You can benefit also from, let's say, data control, so it could be for privacy issues. So if you deploy this operator, for example, at the edge or in the fog infrastructure, you have new issues. These new issues are, for example, if your user is moving. What happens in that case? You want your application to follow your user, but you're not, you know, administrating the different clusters you want to use. So basically, I've deployed my application using Kubernetes infrastructure. I'm moving, and I want to redeploy my application, but on Mesos infrastructure. So how can I do that? So our proposal has been to propose DSL. So we are starting from the programming language approach. So we are proposing, in fact, a new way of annotating your applications, so that you can easily recompile, re-orchestrate, redeploy your services without to redevelop your application. And doing this, in fact, we provide also synchronization abstractions so that we can avoid, for example, single point of failure. So let's take an example. You are developing an application. So classically, you are using variable. So it's something you want to store. And you have also functions, methods that you want to do your processing. And the idea is to include annotation, such a service, to decide which part of your code will belong to a service, so that this part will be aggregated together, will be compiled and deployed in a single way. So with this kind of annotation, you can decide of the granularity of your services. It could be a function, or it could be several functions. And you can decide also of how you place your data according to your functions. So this is something you can decide as a developer, or this is something that could be automatically added to your code. And it's a pre-processing of your code, so it's not influencing the way you're coding. We provide also modification of the synchronization abstractions. For example, I will just give you an example. Right now, for services, the classical way to communicate is to use message broker. But each time you are developing an application, finally, if all the application use a message broker, you are just creating a single point of failure inside your system. So if your message broker is broken, so finally all your applications also are broken. So when in fact we are processing and redeploying our services, we are generating all, the boilerplate you need to do your service synchronization and interaction. And we can do that directly between the services. So instead, if we need to, instead of having a single point of communication. So we have tested our system against, for example, OpenFaaS, which is a classical FaaS service execution, and in fact we are saving time between services just because we are not going all through the message broker. And the more important point, in fact, is that where OpenFaaS can face a limit in terms of service availability, in fact, our system just can push these limits. So this test has been done using Kubernetes cluster on Raspberry Pi, and the idea was to have limited resources on purpose to show that when we are using classical FaaS framework, in fact they are facing this limit quite easily. So we have different ongoing projects with different companies. So for questions later. So we are working on So automatic service deployment in dynamic environment. We are working on also service reorchestration by formally checking application properties. We are working on also service virtualization, but in specific application domain, so for automotive application. So the idea is to deploy Docker and Kubernetes inside a car. And inside a car, in fact, you don't have classical CPUs. You have ECU, and you have no way of re-implementing Kubernetes. So we will try to, but it's not that easy. So what's in terms of future work? So the idea is to work on how can this dynamic environment influence the infrastructure we will have at the border of the network. And one, let's say, key application we have right now is artificial intelligence. Machine learning is using a lot of resources. Right now, we are using clouds to provide these resources. But the next step is how can we use this border infrastructure for AI? So I will just show you, let's say, our future ideas, your future trends, and I hope it will guide for questions. We are working on Edge AI, so how to analyze data flow in edge infrastructure. And our questions are, okay, how can we provide services that are not only computing, but are sensing at the same time? So it was like the previous presentation, when you use a traffic to monitor the traffic at the same time, finally, any kind of network services could be used as a way of sensing your environment. Inside this network traffic, how to discover patterns. So, because in fact we are grabbing data from the environment, and how can we analyze patterns inside this data flow without having all this data in fact stored in the cloud to be analyzed. And in the same way, we have this 5G. We have this slice mechanism where you can, book your resources. How can we do exactly the same for our computing services? So how can we have, for example, mobile services at the edge? And how can we ensure roaming? How can we do that in a multi-tenant way and guaranteeing quality of the service at the same time? So there are many application domains for this, asset tracking, handling cyber attacks. So right now, for example, cyber attacks, you handle cyber attacks at the destination. So you are using a big firewall, okay, to prevent you from the network traffic. And we can do, in fact, in another way. So prevent cyber attacks at the source. When in fact the traffic is starting, you can analyze the pattern and stop the attack before the attack is just started. Another point we are starting to work on is embedded AI. So instead of using an infinite amount of resources we can have in a cloud, the idea is how can we learn, how can we train models, but in very tiny devices. So guaranteeing at a low carbon footprint, low energy footprint. So right now we are working with ESP32 to do some machine learning. And finally, we can do a lot of things with tiny things. But what we have to take into account is, okay, how can we take decision under uncertainty? Because when in fact you are collecting your data, store all your data in a cloud, and with an infinite amount of resources, in fact you have finally everything you need to take a decision. But when you are doing some machine learning at the border of the network, you don't have all the information, you have partial information, and you are not sure of this information. And you have also to train your model in an intermittent way. So, for example, you have only a few milliseconds or seconds to train your model. So, also a lot of use cases, anticipating devices, smart routers. So right now you are buying, I guess, Cisco or Huawei routers. So you don't even know, but they already include intelligence inside to analyze your data flow patterns. But the analysis is not done inside the router. In fact, the analysis is done inside the Cisco cloud. Okay, and you are not really aware of what's happening in that case. So smart devices really from having your AI inside. Another interesting use case is predictive maintenance. Right now, in fact, many companies spend a lot of money sending people to repair things, to repair your heater, to repair your building, etc. And from the prediction, in fact, of the behavior of your devices, you can really save a lot of money. And one of the last points is how to do the geo-distribution of your artificial intelligence. So how can we do service handover? So right now it's something we don't even know how to do in a multi-cloud infrastructure. So how can we do that in an infrastructure that we can't trust even? So a lot of open issues. Federated learning, so a way of learning together, so letting different devices learn in a distributed way. But how can we do that using a low energy? And the last point, as IoT devices are quite unpredictable, the question is how can we do that in a fault-tolerant way? Because you are always on battery, and you can always be disconnected, and you can't rely on this system, but we have to. A lot of use cases also. So how can we have cheap, local, yes. So if you want to deploy your own infrastructure right now, it's quite easy to buy the hardware. But in fact, the added value of a cloud is that you don't have to maintain this infrastructure. And if you can deploy, in fact, AI on such kind of infrastructure and predict how it is working, finally, it could be self-managed. Last point about responsibility. So when we are talking about AI and distributed system, somehow we have to consider how can we trust the system, How can we ensure privacy, sovereignty, and the ethical issues? Because as soon as you have AI in your infrastructure, in your OS, it means that this AI will take decisions. But do this decision will be let's say, compliant with your also law regulations, so such as GDPR in Europe, for example. How can we guarantee that the system is respecting this issue? And last point, an interesting point also, because I have never heard for the moment, we are developing systems. And we are developing systems, for people, but different peoples. So, if you are developing a system for an hospital, it's not the same as developing a system for an IT company, or it's not the same as for a manufacturer. So inside a system, inside an application, in fact, you have all these job issues that are really only for this kind of sector. And in fact, you need to take this information into account when you are taking a decision. So how to integrate ethics, job ethics inside the AI and inside your infrastructure. So, for example, if I'm assisting a doctor, it's not the same as, assisting a driver in a car. You're not the same issues. So, plenty of open questions. I would be very happy to discuss with you. Thank you.
Thank you. A lot of open, very interesting questions. And we also have several questions in Slido. So, the first one, can you give an example of a cyber attack that can be stopped in the beginning, as you mentioned? Doesn't the attacker have almost full control of the router?
In fact, for right now, the great DDoS attacks we have in the last years. These DDoS attacks have been starting using IoT devices that were compromised. Cameras and different open devices. Why? Because this device, in fact, the OS, the firmware on this device are not maintained at all. So you have security issues, and they well know we have security issues, but it's not patched, And so probably it means that at home, you have IoT device that you don't control, in fact. And the way where we can control is because your traffic is going through a gateway, is going through a router, and in this point, if this point is not compromised, and for the attacks, these points are not compromised. If at this place you can check the traffic, then you can stop the attack at this point. So attackers are not controlling all the infrastructure.
Right, yeah, thank you. Since you mentioned DDoS attacks, that leads us to a second question. Is there a prevention from DDoSing the analysis in the cloud by crafting weird payloads that can take a lot of time to process?
Oh, I don't know. I don't know. So
probably another open research area.
Yeah, I think I don't have all these data, so that I can't say if it is possible or not.
Right. Okay. Thank you. And the last one is more question or a recommendation. Do you know a lightweight implementation of Kubernetes called K3S? Could it be useful for your use case?
Yeah, for sure. We are using it also. Yeah. It's a light implementation of Kubernetes, And yeah, we already use it. You already use it, in fact.
Okay, that's all for the questions in the chat. Actually, I have one myself. Didn't have time to write up. You mentioned using data flow analysis in this distributed environment. Can you apply the same traditional algorithms for data flow analysis that we know from analyzing, software programs, or has it to be something completely different?
I think we can use exactly the same algorithm, but each time we have to specify it according to your application domain, data flow, etc. So each time you are considering an application, especially in IoT, in fact, it's a different application. And this is the problem, in fact. I guess you have already tested. Each time a company is developing an IoT application, in fact, it's deploying its own IoT infrastructure. And you have several infrastructures, IoT devices, protocols. So for the moment, we are far away from having standards for IoT.
Okay, thank you. Thank you for responding to questions. Thank you for your presentation.